and somehow limit it. And if you find any trigger while you're scanning, if you find a closed port, for example, use it and discard the fallback triggers. Okay, so now we come to the fun part after lots of theory, which is the race between Port Bunny and Nmap. First, we're going to race on responsive hosts, because that should be a field where Nmap should be a lot better, because we're actually sending 10% more data because of the triggers. So the question is, can we still win or can't we win? Let's just see. Okay, of course, nothing's for free. But to be honest, when I fixed the slides today, I was searching for, desperately searching for a host where Nmap would actually outperform us. And this is what I found. What I did was I plugged a cable directly to my OpenWrt, and in that situation, and I made sure that all the boxes in the apartment were not running, and in that situation you can't do much wrong. And then in fact, Nmap beat us. They had 30 seconds, and we had 32 seconds scanning all ports. But that doesn't count much, because, you know, one little bug, or you know, just maybe somebody else is using the network, something like that, and you already have the big differences. 41 seconds for Nmap here, 28 seconds for us. Basically, well, this is not exactly the same setup. This is where we're scanning over the internet, so this is where it gets a little more complicated than if you just plug a cable between your home router and your box. And Port Bunny just really often just wins this race, which is kind of pathetic because, like I said, it sends 10% more data. So here's 30 seconds for Nmap and 25 seconds for Port Bunny. And then there are serious bugs in Nmap. And I think that's, that problem arises when you try to, you know, have 23 different scanning types and you all plug them into one, you try to plug them into one timing code, then you get things like this. If packet drops are particularly bad, enforce a delay between packet sends, useful for cases such as UDP scan where responses are frequently rate limited by destination machines or firewalls. And that basically translates to, if packet drops are particularly bad, break the complete timing concept. Because if you're enforcing delays between your sends, then what you're regulating is not really the number of packets out there in the network anymore. You can see this here. We were scanning the iPhone, which was really fun. You'll be thinking, oh, Nmap, the iPhone is obviously a performer. Lots of traffic there in the Nmap graph. But if you look very closely, then you'll see, I'll show you, this small little gap there right after the start, okay? Can you show it? Yeah. Yeah, that gap, right. That is where packet drops were particularly bad. And now a scan delay was enforced, which means that now the scan delay is actually bigger than the round trip time, which then means that we're sending less than 1 packet per round trip time, but we're increasing what we think is the number of packets out at once to really high levels, but really we're just sending less than 1 packet at once. And on the other hand, there's the Port Bunny graph, where you see that there's obviously a limit that's easily detected at about 20 packets or so, and we keep on hitting that, and then, you know, just scanning at a pretty constant speed. And the difference is 24 minutes for Nmap and 8 minutes for Port Bunny. Okay, almost done. How much time is left? Enough? Okay. Scanning in parallel. if you Google for port scanners, you'll find a couple of you'll find a port scanner which says, I scan in parallel, and if the port scan goes too slow, then you'll have to scan more jobs in parallel. That's nonsense, and I want to tell you why. The question is, when will parallel scans win, and will they always win? And the assumption is usually, yeah, if we scan in parallel, we're going to be faster. But that's not always true. You have to identify the bottleneck you're dealing with. There are so-called shared bottlenecks among all scan jobs, which basically means, well, yeah, for example, you have a DSL connection, and you just can't go faster than the DSL connection, so yeah, that's shared among all scan jobs. Then the bottleneck can be shared among some scan jobs, and then there's a so-called target bottleneck, which means which is usually a printer or an iPhone or something like that, just a device which can't handle the traffic that you're giving it. So obviously, if you have a shared bottleneck, there's no real gain in scanning in parallel. That's because a single scan job can make full use of the capacity that's there. And in fact, if you have more scan jobs, then they will fight for the connection, and they will generate losses, and you'll actually go slower than you would have if you had just scanned sequentially. This, of course, assumes that your congestion control algorithm is actually implemented correctly and also works for filtered hosts. Because if it doesn't, of course, then the scan jobs which are scanning filtered hosts are basically they're performing at a very low level, so then it makes sense to scan something else while you're doing that. Now, if you have a target bottleneck, then scanning in parallel makes sense. But that's a lot less frequently the case than just having the DSL connection be the bottleneck. So what does Nmap do? Obviously, it doesn't implement the congestion control scheme for filtered hosts correctly. So what it does is it basically performs the same scheme that it has applied to each of the hosts to the shared bottleneck by counting all responses and all drops. And then you may only send, wait a minute, we'll slow down, yeah. It will only send if both the global system allow it and the timing for this specific host. But that has a lot of problems. One problem is that a badly performing host will keep good performing hosts from firing, which means that this is extremely biased towards the worst performing scan job. And then again, you're not timing the number of packets out at once anymore, because you're keeping scan jobs from maintaining this number of packets out at once. So again, you've broken the concept of the algorithm. So that's not good. So Port Bunny's solution is, since we can actually do these congestion control schemes for all possible hosts, and they have been designed for lots of jobs to be run in parallel, what we do is, in most cases, because of the shared bottleneck, we will scan one host at a time. But you have the option of just saying, I want more hosts now, and then it will just use these. It will just use the timing for each host independently. So there's a lot more research which can be done in parallel scanning. For example, the algorithm which we're currently using, TCP Reno, with the one that goes back to the 80s, needs to generate losses to actually find the capacity of the network. And of course, that's not very efficient. And then there are new algorithms such as TCP-Vigas, which measure the change in round-trip time. That, for example, could be implemented, and the question would be, does this perform nicely, especially if other, network traffic is using TCP Reno, because that's a lot more aggressive. And this is one reason why Port Bunny is in the kernel. We need extremely precise timing for these kinds of things, for measuring changes in round-trip time. Right now, we're not really doing that, but we're aiming at doing that. And also, we wanted to address the scanner bottleneck issue. But to be honest, the kernel is a good place for a port scanner. But for what we're doing right now, I don't think we would have had to do this. But like I just said, it's not a bad place for the port scanner at all. For example, you get a sniffer for free, and this is a quite funny story, so I wanted to tell you. What you can do in the Linux kernel is you can register a callback function, and you can basically register this at the beginning of the chain, which all Ethernet frames must pass. And so that's what we did. So all Ethernet frames first go through the Port Bunny receive function, and we can choose to drop them or just do things with them and then pass them on and whatever we want to do. So you just get the sniffer for free, and it's really nice. And last, but I wanted to tell you about the user's perspective, because we made Port Bunny we made it look like a device. We have a device file, and you can basically echo and cat your messages into there, and the protocol is quite simple. Looks something like this: create scan job, whatever, and then set ports to scan and execute it. And then the output would look something like this. So you get the port results straight away. But don't worry, we also wrote a UI, so you don't have to use this echo and cut into the device all the time. It's very simple. You just give it the host, and it starts scanning it. You have a bit of interaction. You can abort the scan job if something goes wrong. You can increase the number of jobs which is scanned at the moment. And about the command line, what's very nice is the /g flag, which generates you data for GNU plot. So the plots that I showed you were all made like this. Thank you. I forgot to tell you about the release. We're going to release this in January, but you can already get a tarball from me directly if you want one. The problem is just that we're still dealing with the licenses and all, so yeah. But it's going to be free for people who can't release. It's going to be free, yeah.